In this video, we're going to talk about significant digits, also known as significant figures. So what is a significant digit? Let's say we're given the number 4.72. This number has three significant figures. A significant figure in a number represents either reliability or necessity in that number. So what does reliability mean? Well, let's say this number represents a measurement that someone took with this ruler. This is in centimeters, so 1 centimeter, 2 centimeters, 3 centimeters, and each tick is a millimeter. And let's assume that this is a professional measurement. The person is doing the best they can to give you the most accurate measurement they can, and they're skilled at taking measurements. So we can interpret this as the length of what was being measured was 4 centimeters plus 7 millimeters plus some fraction of a millimeter. And the person measuring felt that that fraction of a millimeter fell closer to the 4.7 millimeter tick mark than the 4.8 millimeter tick mark. Now, if someone else took the measurement and got 4.73 or 4.74, 4.71, maybe even 4.75 or 6, is that wrong? Which one's right? They're all right, because it's subjective where exactly the measurement lies between the 4.7 and 4.8 millimeter tick mark. So even though this 2 is uncertain, it's still significant. Now, if we were given the number, well, there's no way you could report this digit from a measurement with this ruler. So it wouldn't make any sense to have this as a significant figure for this number. So you leave it off. And so this significant figure represents the reliability of the number. How precise is the number? How uncertain is the number? Now, if a significant figure doesn't represent reliability, then it represents necessity. So this 4 here, what we need to know is the length of whatever's being measured 4 centimeters, 5 centimeters, 7 centimeters? Well, at least in that range. Is it in the range of 4 centimeters, 3 centimeters? Same here, right? You can think about it like, is it in the range of 45 millimeters, 50 millimeters, 53 millimeters? That represents necessity for the application. So that's what a significant figure is. How can we count the total number of significant figures in a number? Any non-zero number is a significant digit. These are non-zero numbers. So this has 3 significant digits. Each one of these is non-zero, 4 significant digits. So any non-zero digit, whether or not the number has a decimal, if there's zeros around the number, it doesn't matter no matter what. If it's non-zero, it's significant. 9, 1 significant digit. Okay? Next, if you have a 0 that's sandwiched between 2 non-zero digits, that 0 is significant for any case, no matter what. If the number has a decimal point, doesn't have a decimal point, no matter what, a 0 sandwiched between 2 non-zero digits is significant. Okay? This is significant. This has 3 significant digits. Okay, this is sandwiched between 2 non-zero digits. All of these are non-zero. So 1, 2, 3, 4. Right? This is the first time we've had a number with a decimal point, but all of these rules have nothing to do with whether or not the number has a decimal point. All of the rules we've talked about so far. Non-zero digits and zeros sandwiched between 2 non-zero digits. All of these digits are significant. You have non-zero digits and zeros sandwiched between non-zero digits. So 1, 2, 3, 4, 5, 6, 7. Okay, so far, easy, right? What's another situation where you're guaranteed to have a significant digit? If you have a number with a decimal point, absolutely any number with a decimal point, trailing zeros are always significant. So these are trailing zeros, right? We have a number with a decimal point, trailing zeros. So these 2 are significant. So we've got 1, 2, 3, 4, 5, 6. Okay? This is a number that has a decimal point. We've got non-zero digits here and a trailing 0. This 0 is significant. 1, 2, 3, 4, 5. Okay, we have a negative number here, but when it comes to significant figures, negatives don't matter. Negatives don't come into play with counting significant figures. All right, so we've got a number with a decimal point here, and we've got 4 trailing zeros. All 4 of these are significant? Yes, they are. 4, 5, 6, 7. If we had 50 trailing zeros, all 50 would be significant. Okay, what about this? Okay, we have a number with a decimal. We have a number with a decimal point. Nothing's changed. It's just a number that has a decimal point in it. Trailing zeros are significant. 5 significant digits. What about this? This is a number with a decimal point. Is this a trailing zero, though? Again, these are trailing zeros, but is this a trailing zero? Yes, it is. Trailing means it's at the end of the number, regardless of the decimal point. This is a trailing zero. It trails all of the other non-zero digits, no matter where the decimal point is. So all of those zeros are significant. 1, 2, 3, 4, 5, 6. So even if we had these are all trailing zeros. These are all trailing zeros, and we have a number with a decimal point. 1, 2, 3, 4, 5, 6, 7. All 7 of those zeros are significant. So we have the 8, so 8 significant digits. What if we have, okay, this is a number with a decimal point. These are trailing zeros in a number with a decimal point. So we've got 3 significant figures. Okay, now, when is a digit not significant? For any number with decimal point or no decimal point, leading zeros are never significant. So there's no decimal point in this number. These leading zeros are not significant. This only has 3 significant figures. Okay, there's no decimal point. This 0 is sandwiched between 2 non-zero digits. That's significant. These leading zeros are not significant. But even if there is a decimal point, it doesn't matter. Okay, this is a number with a decimal point. Decimal point or no decimal point. Leading zeros, these are leading zeros, are not significant. This trailing zero is, though. Okay? Leading zeros for any situation are never significant. This has 1 significant figure. Okay, so we've covered every scenario that you can come across except for one. That's when you have trailing zeros, but there's no decimal point in the number. So what if you have the number 4,000, no decimal point? Are these zeros significant? The answer is we don't know. But if you're asked on a test and you have to give an answer, then just say they're not significant. So what do I mean by we don't know? Well, you can think about it this way. There's 3 different scenarios we can consider for possibilities of where this number came from. If someone took a measurement or a count of something and got 3,521, and they decided to round this up to 4,000. Well, then there's only one significant figure here, the 4. These zeros aren't significant. So the answer would be one significant figure here. What if there was a situation where someone got the number 3,961 and they weren't rounding the thousandths place like they did here? They were rounding the thousandths place up because of this 5. They were instead rounding the hundredths place. So in other words, if they had, this would be rounded to, right? They rounded the hundredths place, but here they round this 9 up, but that results in the thousandths place going to 4. Well, now we have 2 significant digits. This 0 is significant. Same exact number, but 2 significant digits here. Okay, now let's say we have, and we're rounding to the 10th place. Well, this gets rounded up, and it makes its way all the way to the thousandths place again. Now we've got 3 significant digits. So if you have a number without a decimal point, with trailing zeros, you really don't know how many significant digits there are. But if you have to give an answer, the answer would be that those trailing zeros aren't significant. Because I guess you can assume that if the person who gave the number didn't feel the need to specify that they were significant, then they probably aren't significant. So here we would say this has one significant digit. Okay, trailing zeros, no decimal point. These aren't significant. 1, 2, 3, 4. This 0 is sandwiched between two non-zero digits. Okay. I don't know why you would ever write a number like this, but leading zeros are never significant. Trailing zeros with no decimal point aren't significant. So just 2 here. Okay, we've got trailing zeros, but we have a decimal point. These trailing zeros are significant. These leading zeros aren't. 1, 2, 3, 4. So for this 4,000, I mentioned that you could argue that since whoever gave this number didn't feel the need to specify how many significant digits there are, then you could assume that these zeros aren't significant. Well, how would you specify if there are 1, 2, or 3 significant digits here? Well, that's one of the purposes of scientific notation. With scientific notation, you can specify how many significant digits are in a number. Now, I have a whole separate video on scientific notation. I'll put a link to the video in the description. But if a number is properly written in scientific notation, per the definition of scientific notation, then no matter what, every digit is going to be significant. So, as we talk about in the scientific notation video, for scientific notation, you're always going to have a single digit to the left of the decimal point, a single non-zero digit to the left of the decimal point. So this will be a 1, a 3, a 7, something from 1 to 9. And you could have a negative as well if you want. But the number won't be greater than 9. Like you can't have a 11 or a 12. It has to be a single digit number from 1 to 9. So here we would have a 4. You'll always have this. For scientific notation, you'll always have this. You can't have no number either. Like you can't have scientific notation and have times 10 to the something. You can have no number either. You have to have a number. So with that in mind, what do you notice? Well, with that restriction, no matter what we write now, every single digit is going to be significant no matter what. Because trailing zeros for numbers with decimal points are always significant. So what other options do we have? Non-zero numbers or zeros sandwiched between non-zero digits. So like here, 4.00, and we would put what? Times 10 to the third. So that's 4 significant figures. You see? But okay, like if we wanted, for the case where we rounded, it was like 3,900, right? We rounded in the tens place. So if we rounded this up from the tens place, we could still round this to the thousands place. We could do that. We could be rounding up the 3, but let's say we were rounding up this 9 here. What we would present the number as this: 4.00 times 10 to the second. That's 3 significant digits. Okay, if we were rounding up to the hundredths place, we would do, or no, this would be times 10 to the third. And then this would also be times 10 to the third. So now you have 2 significant digits, right? And if we were rounding up to the thousands place, we would just say, we could just do this. You could do it like this, or you could put a decimal point if you want. It's probably better to do that. So this has 1 significant digit, you see? So if you're ever asked on a test or wherever to count the number of significant digits for something that's given in proper scientific notation, then just count the digits. Okay, now let's take some values and write those values with different numbers of significant digits. So if we've got okay, that's the raw number. You can think about this as a measurement you took and you just wrote down all the digits. Or you got this out on your calculator, you wrote down all the digits that it gave you. But now we want to present it with a certain number of significant figures. To do this, we're going to need to round the number. This is where rounding comes into play. So if we want to write this with one significant figure. So right now we're kind of treating these all like they're significant. What you do is you keep the most significant digit and make the other digits insignificant by making them 0 or just removing them. And so amongst these significant digits, the most significant is the one with the highest placeholder exponent. So this is 10 to the third, the thousandths place. This is the most significant. So since we're rounding to one significant digit, we're going to round this number and keep it as significant. We wouldn't round the 7 and make this 0 here, right? We're going to round this and keep it. So you come to the number before the digit you're rounding. If it's 5 or greater, then you round your number up. If it's 4 or less, then you keep the number as is. So here, this rounds up to 6. And there's our one significant digit, and the rest becomes 0. Or in this case, we don't write these two at all. You don't put this because now all of these are significant. Now we talked about this is kind of ambiguous because we don't know if these zeros are significant or not. So we probably should write this as 6 times 10 to the third. Okay. What if we want to write this number with 2 significant digits? Okay, so we're treating all these as significant at the moment. The first significant digit that we're going to keep is the most significant. The next most significant is this 10 to the second place. So we're going to keep these two and round off this one. So before this number is an 8, greater than or equal to 5, so we round this up to 8. Okay, so we should probably put this in scientific notation. 2 significant digits. Okay, 3 significant digits. We're going to keep these 3. The number before the 8 is less than 5, so we just keep the 8 as is. Okay, writing this in scientific notation. This has 3 significant digits. Okay, what if we want to present this number with 1 significant digit? Okay, we're going to keep this digit here, come before it, round up. This is greater than or equal to 5, so round this up. Minus 600. But to avoid confusion, let's put, this is 1 significant digit. What if we want to present this with 2 significant digits? So we're going to keep these 2 digits. Before the 6, we have a 1 that's less than 4. So now this is 2 significant digits. 3, these are the most significant 3 digits. The highest placeholder exponent, 10 to the third, 10 to the second, 10 to the first, and this is 10 to the minus 1, so we're keeping these 3. Come here. Before this, you have a 1. It's less than 5, so we're going to keep this as a 1. So this, you don't have to write in scientific notation. It's clear that there's only 3 significant digits, but you could do this if you wanted to. Okay, 4. We'll keep these 4 digits. There's a 0 here, so we're going to keep this number as it is. You can leave it like that. That's 4 significant digits. And just to change it up, let me put a 7 here. Okay, so 5 digits. We're going to keep these 5 digits. So coming here, we look before this digit. We find a number that is greater than or equal to 5, so we're going to round this up to 1. That's 5 significant digits. Okay, let's present this number with 1 significant digit. Well, okay, we've got, just as it sits, How many significant digits do we have? These leading zeros are not significant. We've got 1, 2, 3, 4, 5. 5 significant digits. What is the most significant of these 5? Well, the highest exponent, placeholder exponent, is this 10 to the minus 3. That's greater than 10 to the minus 4, 10 to the minus 5. So we're going to round this digit. Okay, we come before it. We see an 8 that's greater than or equal to 5, so we round this up to 3. Okay, that's one significant digit there, right? You could do it 3 times 10 to the minus 3 as well. Okay, we want to present this with 2 significant digits. We're going to keep these 2. These are the most significant digits. Come here to the least significant digit of the digits that we're going to keep. We're going to round that one. Before it is a 0, so we're going to keep this as an 8. Okay, that's 2 significant digits. Or you could do, all right? We're going to keep these 3 digits. Come to the least significant of those 3. Before it we see a 1, we're going to keep this as a 0. Right, now we have 3 significant digits. Or you could do, this also has 3 significant digits. Okay, if we want to present this with 1 significant digit, so we're going to keep the most significant digit and round that digit. So we have a 2 here, so we're going to leave this as a 4 and make the rest zeros or just remove them. All right, but to avoid confusion, we'll say 4 times 10 to the 1, 2, 3, 4, 5, 6. So this is clearly 1 significant digit. We're going to keep these 2 digits, then round the least significant of those 2. We have a 5 here. We're going to round that up to a 3. We can present this way. Three significant digits. We're going to keep these 3. Round this third. There's a 0 here. We're going to keep this as a 5. Four, we're going to keep these 4 and then round the least significant of those 4. There's a 0 here, so we're going to leave this one as it is. So this illustrates that ambiguity, right? We got the exact same number here. But this one has 4 significant digits, this one has 3. But there's no ambiguity if we do it like with scientific notation. Okay, 5. We're going to keep these 5. So now I just want to point out regards to rounding. So the most general method, where if we're rounding this 2, if the number is greater than or equal to 5, we round up. If it's less than 5, we round down. There are other methods. So there's a method that says you still use that same rounding rule, that greater than or equal to 5 or less round up, less than 4 round down. You use that if the digit, not the digit you're rounding, but the digit you're evaluating on whether or not to round your digit up or down. So like the way it's described is you have the nth digit is the digit you're rounding, right? So we're talking about the nth plus 1 digit. If that digit is greater than 5, no matter what, then just round up. If it's less than 5, then just round down. If it's equal to 5 and there's numbers after that nth plus 1 digit, numbers other than 0, then do the standard round up. However, if you have a case where the nth plus 1 digit is not followed by other digits or it's only followed by zeros, then you use the rule that if the nth digit is an even number, then the digit is not rounded up. So here you would say this is rounded to 4.2. If it's an odd number, then this is rounded to 4.4. And apparently this avoids skewing the average value of a long list of values upwards. I don't know, just wanted to point out that there are other variations in rounding technique, but I would just stick with the standard, most accepted method that we did all of our examples with. You might come across a different method. So for example, the engineering mechanics textbook that I have, so Statics and Dynamics from Hibbler, written by Hibbler, in the opening chapter, he talks about how you should round using this technique here. But in general, I would just round with the standard technique, that we used. So no matter what the case, if you have the number preceding the number you're rounding is 5 or greater, round up. If it's less than 5, round down. All right, now we're going to talk about if you add, subtract, multiply, or divide two numbers, how do you represent the final answer with the appropriate number of significant figures? So let's say you're adding or subtracting two numbers. Let's say we've got 4.395 plus 7.86. What you want to do is first write the addition out vertically and align the two numbers based on their placeholder exponent. So we've got, so this is the ones place. So align the ones place of this number with the ones place here. And then align the 10 to the minus 1 with the 10 to the minus 1, 10 to the minus 2 with the 10 to the minus 2. Now the next thing you want to do is perform the addition and just keep the maximum number of digits. And don't put like a 0 here, because that can be confusing, because now you've added an extra significant digit, but we're still keeping track of significant digits. But first we're just going to add these two numbers and keep the maximum number of significant digits. So we've got 5, 9 plus 6 is 15. Carry the 1. 12, carry the 1. We've got, next we want to round this number. How many significant figures are we going to round this number to? Well, you compare the two numbers and you keep the smallest placeholder. So for addition and subtraction, it's not about the number of significant digits. It's that you don't keep a larger level of precision than the number with the smallest level of precision. So we don't keep this digit here. We keep this digit. So we're going to round this to 6. Okay? Let's try 5.72 plus 3.1. So first, write the addition in vertical form and line up the placeholder location of each digit. So we'll put the tens lined up vertically. But don't put a 0 here, because you can add that way, but we're trying to track significant digits of each number, so you don't want to confuse yourself. Okay, now add the two numbers. First, just keep the maximum number of significant figures. So 2, 8, 8, okay? Now come back and see what is the smallest level of precision of the two numbers. Well, that's the tens place, right? So we're not gonna keep this digit. This is the maximum precision of our final answer is this tens place. So we're gonna round. We're gonna get rid of this hundredths place and round this tens place. So there's a 2 here, so we round this to 8.8. Okay, let's do. Okay, this is subtraction, but it's the exact same process. Okay, here just write the subtraction vertically and line up the places. But since this number is bigger than this number, we do minus, and then so put the 2 here. So we'll do this subtraction, and just, this is going to be a negative. Okay, so this is a little tougher because it's tempting to want to put these zeros, which would be helpful, but let's try and do it without the zeros. So we need to borrow here. This is going to be a 10, and then we need to borrow again. So this is a 10. So 10 minus 3 is 7. 9 minus 7 is 2. 7 minus 1 is 6. Okay, we need to borrow here. 13 minus 7 is 6. 8 minus 2 is 6. Okay, so this is we've kept the maximum number of significant digits, but we can see that this number, its precision is only to the hundredths digit. So we're going to keep the hundredths digit. Minus 6.66. We have an evil number here. But this is the correct answer. Okay, so let's write this subtraction vertically. Minus, now we can put a placeholder 0 here because this isn't significant. Okay. Right. Okay, so that's the maximum number of significant digits, but it's also the precision. Both these numbers have the same precision. They both have significant digits in the thousandths place. So this is the correct answer. Same exact process, just write the subtraction, line up the places. So the ones and the ones are lined up here. Perform the subtraction but first leave the maximum number of significant digits. Okay, so we need to borrow here. This is a 10. Borrow here, we get a 10, but just imagine that there's a 10 there. Borrow there, we get a 10. So 10 minus 8 is 2. 9 minus 2 is 7. 9 minus 1 is 8. 3 minus 0 is 3. Okay. Now, what is the precision what is this of the two numbers? Which one has the smallest number of precision? This one. This one is only precise to the tenths place, or to the ones place. So we're going to round this number, the final answer, to the ones place. But for the ones place, you have a 7, so round this up to 539. All right, let's write this out. Okay, 7 plus 0 is 7. 3 plus 2 is 5. 4 plus 0 is 4. 5 plus 2 is 7. Okay, now we're going to round to the tenths place. So there's a 7 here, so we're going to round up to 174.6. Okay, what if we have... All right, same process. Line up the places, and don't put any significant placeholder zeros. It might be tempting to. Don't do it. Okay, so we've got to borrow here, borrow here, borrow here, borrow here. Okay, so 10 minus 3 is 7. 9 minus 3 is 6. 9 minus 2. Okay, so what is the precision of this number is the hundredths place. What is the precision of this number? Is it the ones place? No. You would say that this is precise to the hundredths place. Remember, so how many significant figures 4200 has? It has no decimal, just 4200. It's ambiguous, but if you're going to make an assumption, so like if they're asking you this on a test, then you assume that trailing zeros with no decimal are not significant. So we would say that this is precise only to the hundredths place. So we're going to round this to the hundredths place. Round this digit. So before this digit is a 1, so we're going to write this as 4100. Okay? So we will write the subtraction vertically, line up the places. Okay, but this is going to be a negative in the final answer. So now let's do the subtraction. Borrow here, and then, okay. So now 10 minus 3 is 7, 0 minus 0 is 0, 7 minus 0. This is precise to the ones place. You would say that this is precise not to the ones place, but to the tenths place. You know, it seems like it could be precise to the ones place, but technically this trailing zero is ambiguous. So unless you're given further information, you can a lot of times assume that this is insignificant. So this is precise to the tenths place. We're going to round here. So minus this 4 is a 4 here, so 7070. Okay, what if we have what do? Same process. Just line these up vertically and perform the addition. Okay, now what we're not going to do is like perform this addition first, round it, then perform this addition and round it again. You do all of your calculations with the maximum number of significant digits first, get the final answer, then round just the final answer. Now, how do you round just the final answer? Well, as you're doing those intermediate calculations, you keep track of the significant digits without rounding, and then so you count how many significant digits they're supposed to be at the final answer, but you still don't round at those intermediate steps. So, okay, 5 plus 0 plus 0 is 5. Okay, 5 plus 2 is 7. 6, 7, 8, 9, 10, 11, 7, 8, 14, 18. Okay, so with these two, you kept to the tenths place. And now with these two, you keep the tenths place. I mean, you don't have to keep track. If you're strictly adding or subtracting, all of the numbers are just adding and subtracting, then you're just going to end up keeping of all of the numbers. Even if you're adding 10 numbers, you're going to keep the number that has you're going to round to the number with the least amount of precision. So we're going to round to the tenths place here. So this 7, we're going to round up to 38.2. All right, I'm just going to go ahead and write it vertically now. Okay, we're going to, let's add these two and then subtract this. In effect, we have, okay, now don't put those placeholder zeros. That's going to be very confusing if you're tracking significant digits. But okay, so what we're going to do is do this addition first. Okay, so 2. Okay, now you do not round this. You leave the maximum number of of significant digits. We only round the final answer. Okay, now minus 77.43. Okay, we borrow a, okay, we're going to need to borrow here, borrow here, borrow here, borrow here, and then borrow here. So we've got 7, 2, 2, 9, 6, 5, 2, 4. And again, if you're just strictly adding or subtracting, and if you have multiple steps, like you're adding or subtracting a bunch of different numbers, and it's strictly addition or subtraction, you don't have to keep track of the significant digits at each step. You can just, of all those numbers, find the one with the least amount of precision and then round to that number. But we will have to keep, if we're mixing up multiplication and division, we'll have to keep track of the numbers, and we'll show that soon. But here, okay, here we've got this number, and this number were what we were adding or subtracting. The least amount of precision was with this digit, this 100,000th digit. So we're going to round to this digit. So we have a 5 here, so we're going to round this to a 3, 1, 2, 3, 4, and that's your final answer. Okay, let's say we're adding these 3 numbers. Okay, so do the addition, keep all of the significant digits. Okay, so now we're going to round to, of all 3 of these numbers, which one has the least level of precision? That would be this number, the 10,000th digit. It's precise to the 10,000th digit. So we're going to round to this number here. We have a 6, so we're going to round to 240,000. Okay, one more example. Do the subtraction. Okay, now we're going to round to the 10th place. So this is, we round this to 4.0. Okay, multiplication and division. Let's say we have 425 times 18. So same process, just perform the multiplication and write out the maximum number of significant digits. So 7650. Okay, now of the 2 numbers, you count the number of significant figures, and you keep the number with the least number of significant figures. So this isn't like addition and subtraction where you're looking for the precision of the number. This is strictly count the total number of significant figures in each number, and the final answer is rounded to the number with the least number of significant digits. So here, this has 3, this has 2, so we're going to round this to 2 significant figures. Okay, so 7 times 14, 98. Okay, this has 1 significant figure, this has 2 significant figures, so we round this to 1 significant figure. $5,400 times 230. Okay, this has 2 significant figures. This has 2 significant figures. So we round this to 2 significant figures. We have a 4 here. This 2 will stay as is. 120,000. Okay, so okay, 2 significant figures, 3 significant figures. So we're going to round to 2. 1, 1. All right. $6.825. All right, this has 3 significant figures. This has 2 significant figures. So we're going to round to 2 significant figures. We're not talking about the tenths place. We're talking about just the total number of significant figures. So this is 6.8. Okay. $9,139. Okay, this has 4 significant figures. This has how many? 3 significant figures. We're going to round this to 3 significant figures. Round up this 3 to a 4. All right. $144.415. Okay, this has 4 significant figures. This has 5 significant figures. So we're going to round to 4 significant figures. 44.4. Okay. 57,400. Okay, this has, how many significant figures does this have? I mean, it's the zeros is ambiguous. We don't know, but for a test question, or if you have to give an answer, you would say this has 1 significant figure. This has 3, so we're going to round this. We're going to round to the most significant figure, which is the significant figure with the highest placeholder exponent. So this is the most significant figure. We have a 7 here, so round this to 60,000. Okay. $650. Okay, this has 2 significant figures. This has 1 significant figure. We're going to round to 700. All right. $405,604. Okay, this has 4 significant figures. This has 3 significant figures. So we're going to round to 0.406. Right, so we're dividing now, but remember, division and multiplication in terms of significant figures is exactly the same. All right. Do the calculation and keep the maximum number of significant digits that your calculator can hold. 0.000285. Write them all out. Then round. Once you get the final exact answer with the maximum number of significant digits, then you round. Okay, this has 3 significant digits. This has 1. So we're going to round to 0.000. We're going to round to the most significant digit. We're going to round the most significant digit. These are the 3 significant digits. This is the most significant. Okay. Seven eight seven one 5.4. Okay, 3 or 4 significant digits here and 2 significant digits here. So we're going to round this to 2 significant digits. Okay, so now what if we have... Well, okay, first do the multiplications and divisions. 1666.67, another sinister number here. Okay, and this is similar to when we did a bunch of addition and subtraction, you know, like three or four additions or subtractions at the same time. For multiplication and division, though, look at all of the numbers. This has 1 significant digit, this has 1, this has 2, so we're going to keep 1. So round this to 2,000. If it's mixed, if you have multiple steps, mixed addition, subtraction, multiplication, division, that's going to be a little different. We're going to work an example of that soon. Okay. All right, so 1244, 3 significant digits, 2 significant digits, 2 significant digits. So okay, 5737 divided by 72.5. 79.131. 4 significant digits, 3 significant digits, so we're going to round this to 79.1. Now, what if we have mixed multiplication, division, addition, subtraction? So what if we have... Well, okay, you do your order of operations, right? So we're going to do the multiplication first, and then we'll do the addition. But what you want to do is, I'm going to put this into the calculator because this is not a video talking about how to multiply and add. But if you're doing it by hand or with a calculator, you save the maximum number of digits on each intermediate step. So we're going to do this. We're going to say 7.35 times 4.625, okay, and then just leave that number as it is and keep going, plus 7.34. Okay, now we're going to write out this full final answer, 41.3338. That's like you could call that the exact answer. Then we're going to come back and track each of the steps. So here, we did this multiplication. We're left with, this has 3 significant digits, this has 4, so this would have 3 significant digits. Okay, now, but then we're adding here, so it's a little tricky because, all right, if this has 3 significant digits, well, okay, we need to come back and see with 3 significant digits, this is going to be precise to the 10th place. You see? After we did this multiplication and we kept 3 significant digits, this would be precise to the 10th place. So we're adding something with the 10th place, reliability or precision, to something with the 100th place. So we're going to keep the 10th place. So we're going to round this to the 10th place. You see, you don't round this to 34.0 and then add to 7.34. You don't do that. You want to conserve all of your precision. And you might be saying, well, aren't we presenting an answer that's too accurate if we do that, right? Isn't this answer kind of unrealistic? No, it's not. This is like the nominal answer. If you wanted to present this with an uncertainty, you would put plus or minus and put an uncertainty value. And to do the uncertainty analysis, you would go through and see, okay, here, there's an uncertainty based on the rounding, not the rounding, but based on the precision here, you have an uncertainty of this. And then it stacks up, right? You have an uncertainty here that stacks up based on this addition, and you get the total net uncertainty, and you put that here. But that uncertainty is centered about the nominal value. This is the nominal value. But we'll do another video on uncertainty analysis. Okay, what if we have... Okay, so let's just put this into our calculator. 5.25 minus 7.83 divided by 14.92. So negative 0.172922. All right. Now, if we come back, we see that we're going to have a number that's precise to the hundredths place. Well, okay, let's come here. We get in this intermediate step, we get negative 2.58. That has 3 significant digits. So this division here, we've got 3 significant digits and 4. So we're going to keep 3 significant digits in this final answer. So minus 0.17 and then round this to 3. All right. Okay. $59.9834. Okay. Now, in this intermediate step, we're going to be rounding to 5,200, which is interesting. We're going to get 5,200 plus 18.56. We get the same number. That's interesting. As far as significant figures goes, that's the way it is, right? Because this is precise to the hundredths place. So we round to the hundredths place, and we're going to be rounding to keeping this as a 2. So we've got 5,200 divided by 87. That's 2 significant figures divided by 2 significant figures. So we round this to 2 significant figures. Okay, so let's do 18.28 minus 4.3, but then we'll evaluate this because we need to track our significant figures. Okay, now plus 28. Okay, now divided by 15. 2.79867. All right. So with this 18.28 minus 4.3, we keep the tenths place. Well, okay, actually, we could have just done all 3 of these operations at the same time because we're just going to keep the tenths or the ones place. So this 41.98 is going to be kind of like a 42. It's going to be precise to the tens place. So we'll have 2 significant figures there, dividing that by 2 significant figures. So we're going to round this to 2 significant figures. So we've got 7.314 times 860. Okay. Then we've got, let's do this separately here so we can see it clearly. All right. Now we've got this divided by this. 62.5252. in the numerator, 4 significant figures, 2 significant figures, so this is going to have 2 significant figures. Here, we're precise. The smallest level of precision, or the number with the smallest level of precision, is this 13 in the ones place. So we're going to be effectively kind of rounding this to the ones place. So this would you could think of this like being 101. So 3 significant figures. So 2 significant figures divided by 3 significant figures. We're going to keep 2 significant figures. All right. So let's do this with the calculator, but try and separate everything so we can count the number of significant figures. So 4.831 divided by 2.1. Okay. Now 18 divided by 7.25. Okay, now minus 22.4. Well, let's just do this. 22.4 divided by 17. So then we say this plus this. And you see how it's keeping all of those digits? That's what we want. We want to get an exact answer, 3.46559. Okay, now we come back and, okay, we're going to have to write this out. So we're going to have, well, okay, we did this 4.831 divided by 2.1. You keep 2 significant digits, so this is going to be kind of like a 2.3. All right, let's just put that, but we're really adding the full number, but let's just imagine this for the sake of significant digits. Okay, 18 divided by 7.25, we're keeping 2 significant digits, so 2.5, and then 22.4 divided by 17, we're keeping 2 significant digits, so 1.3. Okay, now all of these have the same level of precision, so we're going to be keeping, with these additions and subtractions, we're going to be keeping the tenths place, so round to the tenths place. Okay. The last thing we need to talk about is significant digits when you're doing operations with numbers that are in scientific notation. So if you have, for example, now I'm not going to talk about how to do this multiplication. We go into detail on this in the scientific notation video, but I want to talk about the significant digits. When you're multiplying or dividing numbers in scientific notation, tracking the significant digits and writing the final answer with the correct number of significant digits is easy. So exact same rule, you count in each number, you count the number of significant digits. So this has 3, this has 5, so the final answer is going to have 3 significant digits. 8.34624. And I'll put a link in the description to the video on scientific notation so you can learn how to do this multiplication. But easy. 3 significant digits in the final answer. Round this to 8.35. All you're doing is you multiply these 2 numbers, and then you multiply the 10 to the 5th and the 10 to the minus 2. This is 5 minus 2. Easy. Dividing is the exact same thing. If we were dividing these 2 numbers, you divide these 2 numbers, write that number out with the full number of digits, and then divide 10 to the 5th and 10 to the minus 2. So that's 5 minus 2. You'd get 10 to the 7th. And then just revise the final answer for the correct number of significant digits. Really easy. So I don't think we need to do any more examples here. Well, let's just do this real quick. So let's say negative 8.0 times 10 to the 0 divided by 4 times 10 to the second. Okay, so minus 8.0 divided by 4 is minus 2.0 times 10 to the 0 minus 2 is minus 2. Okay, we've got two significant digits here. We've got 1 here, so we're going to write this as minus 2 times 10 to the minus 2. Okay, easy, right? Very easy. It's a little bit trickier with adding and subtracting in scientific notation. So let's say you have okay, it's not that it's trickier because the rules are different. It's the exact same rules as we discussed in this video, but where it gets tricky, let's do this, and I'll show you what I mean. So to add or subtract in scientific notation, you first convert the numbers so they have the same exponent. So we'll have minus 3.17 times 10 to the third, and then so we want to make this a 10 to the third, so multiply times 10 to the minus 3, or no, multiply times 10 to the minus 1, but then multiply again by 10 to the 1, so we're multiplying by 10 to the 0, that's 1, so this becomes 10 to the third, and this is 6.2289 times 10 to the first, so 62.289 times 10 to the third. All right, so now we have the same exponent. Now we can do this addition or subtraction with these leading terms here. So minus 3.17 plus 62.289 is, so we do 62.289 and then 3.17. Okay, so 9 minus 0 is 9, 8 minus 7 is 1, 2 minus 1 is 1. 12 minus 3 is 9. Okay, so writing this out with all of the significant digits, we've got times 10 to the third. Okay, so we can, this isn't the final answer yet because this is not in scientific notation, because this is greater than 10. And so that's where this is the step where it gets a little confusing. So we can round it right now, or we can round it after. So like if we converted this to proper scientific notation, we would get okay. And so what do we round, right? Because if you look here, it's like our precision we're limited by the hundredths place. So we're rounding this number. But so what happened here? We're rounding to this number. So okay. We're limited by, we need to round to this placement. This is not the hundredths place. When you think about it in the context of the times 10 to the third, what you have is, it's like 62.289, right? When you expand this with the times 10 to the third, and then 3170. This 7 is the tens place, okay? So if we say like 59 we round here, right? We round this 1 up to 2 times 10 to the third. That's the tens place. This is 59120. That's the tens place. And so here we don't round this 1. We would do, you see, this is still the tens place. 59120, because you're 10 to the fourth now. So you see, you can round it here, then convert to proper scientific notation, and leave that third decimal place there, or you can convert to scientific notation and then round there. It's just going to be confusing because you're going to be, when you go to round, you're going to be seeing there's 2 decimal places, but you're really needing to here to round the third decimal place. And so you can see it might be more confusing. There's a big difference between like this 3 and this 4. And so just be aware of that whenever you're doing problems. You see how it's confusing. But yeah, that's the idea with significant digits. If you like this video, like the video, subscribe if you haven't subscribed, and I will see everyone in the next video.